in an imperative programming language, the order of your instructions are really important. So I just really would like to highlight this before I continue, because it's very, I also like people who are less familiar with computer science to try and communicate, in a way that, in a way that everybody can understand. So, I tell you what, I'm going to invent for the moment some random language, or maybe it's a bit like BASIC. For I equal 1 to 10. Yeah, okay. And then we could do print I, and next, this is not invented, this is a bit like, BASIC, isn't it? Although maybe you would need to put $1 in here, but it really doesn't matter. This is pseudocode. Okay, so you can see in here how this is, if you want to understand what this does, you go, it's set the variable I to 1. And then what we're going to do is move the program counter. Oh, wait a minute. No, you don't think of it that way, do you? Or do you? I'd love to know. Because maybe you look at this and you think, no, this is saying print I 10 times, all the values from 1 to 10. Well, actually, that isn't what you're saying. That is what it will do. But is that what you are saying? Let's be strict about it. If you're using an imperative programming language, you're specifically saying the following. Set I equal to 1. Then move to the next line. Then print I. We won't go into how print is a function, and let's just say, keep it simple. Print I. So it prints the value of I. And move on to the next instruction, which is next, which means go to the beginning of the for loop. And so the program counter is doing this. But when it gets to the second time that it gets to the for loop, it's a little different, because now instead of setting I to 1, it adds 1 to I. That's what these instructions mean. So now I is equal 2. And then we print the value of 2. And so it carries on until I reaches 10, and then it jumps to the end so that it can carry on doing the next thing. So this is imperative programming. And it is exactly what happens inside the CPU, believe it or not. In fact, if you were to write this in assembler, it would actually be pretty trivial. I'll just for fun, I will do a pseudo assembler. We can do the same thing, move 1, I don't know, so many different dialects. Move 1 into address 0. This doesn't need to be a real architecture, right? And then what you do is you'd say, loop, we'll set a loop label, and then we'll do load into the accumulator what's in the address 0. Then we jump to the subroutine print, which just say, okay, sudo. It's going to print whatever is in the accumulator. And then we could do something like load A with what's in address 0, the number at address 0, and we could increment A, and then we can do compare A with 10, and then branch if less than BLT, which sandwiches this piece of code. And you can see we're nearly done our for loop, right? It's like you move. Oh, hang on, there's a bug. After you increment A, we might want to store it again. Restore A into address 0. Oh, sort of more or less. And so now what you've got is, again, it goes here. Actually, it's funny because how simple it is. We move, set that to 0, load it into the accumulator, we print it, then we load it into the accumulator again, because maybe print modified it, and then we can do increment A and store it back, and we check to see if it's less than A, and if it is, then we jump back, otherwise we continue, and it's job done. And there it is, and it's going boom, 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 boom inside. And this is why, if you aren't familiar with debugging and you watch a programmer debugging some code in a debugger, they're repeatedly hitting a key like the F10 key, and it's stepping through all the instructions. And you can be stepping through the instructions at the source code level, which is usually what you do, and not at this level, but in the end it's exactly the same. In principle, it's the same. Now, what's this got to do with concurrent processing? Well, and anything else? Well, one thing is that a great source of bugs is the order of instructions. You know, I can say A equal 10 in pseudocode, A equal 10, print A, right? If I say A equal 10 and I print A, that is going to have a very different meaning to if I print A and then set A equal to 10. That's a rather silly example, but the point is the order of instructions is very important and is a huge source of issues with programming. It's the source of a lot of bugs. Another problem is that if we look at the humble if statement, so I say if, you know, let's do some code to wait for a to press a button while not I'm going to go in sort of C now, while not pressed. Okay, so this would be wait for press. I mean, this is the simplest thing ever, isn't it? Is you wait for pressing a key. There are a few problems with this. The biggest problem is that we're actually checking for the key press here. Now you try something like this in Unity, for example. It won't work. You know why? Because the function pressed requires that it is called every so often in order to actually read the state of your keys. And you can see that if I do this, then the only thing that will get executed is the pressed function. Now, if that particular function doesn't do the maintenance that's required to actually read a key press, then you're stuck in an infinite loop. So what we have here is the problem that we actually want to wait for the key press, but not block the entire system while waiting for a key press. And believe it or not, that's why in Unity the coroutine is very handy, because using that you can actually set up something that effectively does, you know, something similar to this, but without locking up the whole engine and the whole editor, maybe your whole computer, no, but you know, yeah, hopefully not, but you know, sometimes. So the problem. This is such a trivial example, isn't it? I mean, you know, it's like we're waiting for... Because, again, let's look at what this is saying. Yeah, I'll do this in a slightly different way, because then we can introduce the if statement. Because, you know, say the phi programming language is the end of if. So what I'm going to do is just put this like that. There we go. So, and now it's if it's pressed. So while true, so we're stuck in this loop, we also check if the key is pressed, then we exit. So this should wait for a key press. But the problem is, let's think very carefully about what's going on, because the key is checked here. And what does here mean? It means that we only check for the status of the key at the moment that the if statement is executed. In other words, the if statement really does not say when the key is pressed, break from the loop. What the if statement is saying is, if the key is pressed, and be stricter about it, if the key state, the state variable that indicates if the key is pressed, that needs to be updated somewhere else, right? If it is indicated as being pressed at the same moment that the if statement is executed, then break out of the loop by, jumping to the first instruction following it. So I'll say that again. If the button appears to be pressed at the same time that the if statement is executed, then jump to the first instruction outside of the while loop. That is what it is saying. And we don't think about that generally, because that's a mouthful, right? When a programmer is looking at that and describing that, they'll say, oh, yeah, when the key is pressed, it'll jump out of the loop. Yes, that's the intention. But with imperative programming, such a simple intention that is involving time has this additional layer of complexity, because it depends on when the if statement is executed. And how do you know when the if statement is executed? And how do we ensure that everything else can run? So this is a huge, huge issue, and is also the cause of many, many great problems in computer science. One of the examples that I love to consider is simply a light switch. You turn the light on and off by operating a light switch. Just the light switch in your own home is a very simple computer. The switch itself has two states, on or off. So it's actually a bit. It's a binary. You can think of it as a binary bit. And you have the light, and the light turns on and off according to. It's a very simple computer. Now, if you have a staircase and there's a light switch at the bottom and the top of the staircase, and you can turn on and off the light from either side, that's an interesting problem, because it's like, how does it do that exactly? Well, it's actually a computational operation, believe it or not. It's an example of an exclusive OR. Yes, all your homes have an exclusive OR gate in them, and nobody ever thinks about it, but it's there. And basically what it says is that if the light switch at the top of the stairs and the bottom of the stairs are the same, then the light should be off. And if they're different, then the light should be on. And by saying that, it's exclusive OR, and by saying that, it means that whether you're at the top of the stairs or the bottom of the stairs, you can control whether or not the light is on. There. Amazing. Bet you didn't know that you all had exclusive OR gates in your houses. But the thing is that these two switches are not operating in an imperative programming architecture. They just aren't. And you can say when the two switches are different, the light is on. When they are the same, the light is off. So why can't we program that way? And that's exactly what the Phi programming language allows you to do, instead of sitting there and running through a loop. Can you imagine the code for this? Like XOR gate? I suppose. You could sit there in a loop and go, read the bottom switch, read the top switch, do an exclusive for, and send that state out to the light. And it sits there in a loop and does this. And yes, it'll appear to work. You turn on and off the light, you know, from the switches, everything seems fine. But internally, it's sitting there going, zzz. It has to periodically check. So you want it to be when, but the computer doesn't understand when. The architecture of our computers only understand if, and specifically if at the moment of the execution of the if. So the Phi programming language gets rid of this problem. So the first thing is, there is no program counter. This means, incidentally, that if you were to build a computer, and I'd love to try, right? If you could, in theory, build a computer that worked with the principles of the Phi programming language, right? And it wouldn't need a clock. Interesting. So,